All right, let's dive right into this explainer. Today, we're embarking on this epic, continuous journey, following a single drop of water through an incredible system that has literally sustained our planet since it was formed. We're talking about the hydrologic cycle, which is essentially just a never-ending loop of transformation and movement. And I promise you, by the time we wrap this up, you're never going to look at a simple glass of water the same way again.
So let's kick things off with a seriously mind-bending question. Are you drinking the exact same water that dinosaurs drank? Well, the short answer is yes, you totally are. You see, the total amount of water on Earth remains almost completely constant. It's not being created, it's not being destroyed, it's just endlessly recycling itself. So that water in your glass today, it actually has a history that goes back millions, even billions of years. Okay, moving right into Section 1, the 4 billion year cycle, an ancient, closed system. The crucial thing to grasp here is just the sheer scale of time we're dealing with. This water cycle has been operating continuously for more than 4 billion years. Since the early days of Earth, this engine has just kept running. And what exactly powers it? It's basically an eternal cosmic tug-of-war between two forces. You have the immense energy of the sun pulling water up, and the relentless force of gravity pulling it right back down. And this is where our journey truly begins. Down in the oceans. An overwhelming 97% of all the water on our planet is locked up in salt water. That leaves a tiny, precious 3% as fresh water. But wait, it gets crazier. Most of that 3%? It's frozen solid in glaciers and ice caps. So the water we actually interact with on a daily basis is literally just a fraction of what's out there.
Let's look at Section 2, the Great Ascent, defying gravity.
It all kicks off with the sun acting as this giant thermal engine. As solar energy heats up the oceans, the lakes, wet soil, or even just wet clothes drying on a line, water molecules start absorbing that heat. They get energized, they move faster and faster, until finally they gain enough microscopic kinetic energy to just break free and escape into the air as water vapor. And, the hotter and windier it is, the faster this invisible escape happens.
Now, here is where biology steps in, and it's honestly so cool. Plants are constantly drinking in water from the soil through their roots, right? But they don't hold on to all of it. Through these tiny microscopic little openings in their leaves called stomata, they actually breathe water vapor back out into the sky. That's called transpiration. Combine that with regular evaporation and you get evapotranspiration. Just imagine a massive forest. It is quite literally exhaling enormous amounts of water vapor into the atmosphere every single day.
Oh, and we totally have to mention this wild atmospheric shortcut called sublimation. Up in freezing cold mountains or, say, sprawling polar regions, water doesn't always bother melting into a puddle first. Instead, the ice and snow transform straight from a solid directly into a gas. It's like magic, just skipping an entire phase of matter to join the great ascent up into the sky.
So, as our water vapor rises higher and higher, the atmospheric pressure drops, and the air gets a lot colder. This brings us to Section 3, Clouds and the Fall, the gathering weight.
Okay, this is a detail that always seems to surprise people. Water vapor actually can't form clouds very easily all by itself. As that warm, moist air rises and cools off, it can't hold as much water. But to actually change back into a liquid, which is condensation, those water molecules need something physical to cling to. They need these microscopic particles floating around in the sky, a tiny speck of dirt, a flake of smoke from a fire, salt from the ocean, even spring pollen. These little particles are basically the unsung heroes of cloud formation.
And as billions of these tiny droplets gather around those microscopic particles, they form the clouds we see every day. It's completely awe-inspiring to think about. When you watch a fluffy white cloud drifting by, the wind is actually pushing around millions of kilograms of floating water. I mean, they look completely weightless, but they're carrying the heavy, life-sustaining cargo for our entire planet. Eventually, through constant collisions inside the cloud, these tiny droplets start to grow. They get larger and larger until they're just too heavy for the cold air to support, and gravity finally takes over. The water plummets back to Earth. Depending on the temperature, it might fall as rain, or maybe it sticks together into delicate snow crystals. It could freeze midair into sleet. Or, in the chaotic updrafts of a huge thunderstorm, droplets can be thrown up and down repeatedly, adding layers of ice until they plummet down as heavy hail.
After that epic, dramatic fall from the sky, our water droplet finally hits the ground. Welcome to Section 4, the underground journey, returning to the Earth. So when water hits the Earth, Some of it rushes right over the surface as runoff, heading straight for streams and rivers, but a lot of it actually soaks deep into the soil, a process we call infiltration. Sandy soils absorb it super fast, while clay is a lot slower. Once it's inside, the water begins to percolate. This is the deep, slow movement of water just squeezing through tiny dark spaces between rocks and soil until it hits these vast underground storage areas we call aquifers.
To put all this into perspective, we really need to look at the staggering contrast in time here. The water cycle doesn't just move at one single speed. A water molecule might sprint through the atmosphere, evaporating, forming a cloud, and raining back down, all in just 9 or 10 days. But if that same molecule percolates down into deep groundwater, it can effectively hibernate down there in the dark for hundreds or even thousands of years before it ever sees the surface again.
Yet no matter how long it takes, almost all water eventually finds its way back to the oceans. Whether it bubbles up fresh from a natural spring, gets pumped out of a deep well by us, or runs violently down a flooded riverbed, gravity tirelessly pulls it right back to the grand collection basin of the sea. And there, 97% of the planet's water waits to just start that 4 billion-year loop all over again.
Let's zoom out a bit now to impartially examine the reality of our current situation. In Section 5, our impact on the cycle, disrupting the delicate balance.
We are fundamentally changing the landscape, and by doing so, we're changing the natural flow of water. When we cut down vast forests, we drastically reduce the transpiration that breathes moisture into the air. When we pave over the earth with urban roads and concrete, water can no longer infiltrate the soil. It just rapidly runs off, which can cause severe flooding. Changing climates alter exactly where and how fast water evaporates and falls. We introduce pollution that contaminates this global recycling system. And by excessively pumping out those ancient underground aquifers, we're artificially lowering water tables and drying up natural springs way faster than they can replenish. We are heavily impacting a system that regulates our entire climate and provides literally every drop of our drinking water.
Which brings us to the end of our explainer today, and I want to leave you with this one final vital thought to ponder. Remember that tiny fraction of fresh water we talked about at the very beginning? When you factor out the ice, less than 1% of Earth's water is actually easily accessible to us in rivers, lakes, and shallow groundwater. The water cycle itself, that's eternal. It's going to keep spinning. But our access to the clean, life-sustaining fresh water within it, that is incredibly fragile, and it depends entirely on how wisely we manage and protect this ancient system today. So what role will you play in the hydrologic journey?